So for number 38, part J, still you have to prepare the buffer, phosphate buffers, 40 liters of 0.02 molar, pH 6.9. But this time, what you are given is sodium phosphate and hydrochloric acid. So sodium phosphate in this case is the solid form. So it's different from the solution that we had in the previous question. So, okay, so what is sodium phosphate? So sodium phosphate. So what does it refer to? So if you put sodium phosphate in water, it will dissociate into sodium ion and phosphate ion. So in this case, it means that our sodium phosphate will give you the PO4 3- form. So in the previous two questions, we starting from the acid part. We starting from H3PO4, but for part J here, we instead starting from PO4 3-, which is the base species here. So to raise the pH to 6.9, because we're starting from base, first you need to change PO4 3- back to HPO4 2-, and then at pH 6.9, you have to further change HPO4 2- to H2PO4-. And this is just gonna be partially changed to H2PO4-. And we can know the amount of H2PO4- by solving the ratio using the Henderson-Hasselbalch equation. Anyway, let's start with figure out how much of sodium phosphate we're going to put into the beaker. So because sodium phosphate is a solid substance, and all the phosphate buffer that we want to make is the phosphate will derive from sodium phosphate. So the mole of the phosphate buffer, we already calculated like many times before. So it's 0.8 moles, right? Using 40 liters times by 0.02 molar. So we need to make phosphate buffer 0.8 moles. But for sodium phosphate, how you can calculate the amount of the solid form of sodium phosphate here. So you need to think about 0.8 moles of sodium phosphate, right? If you want to make a phosphate buffer 0.8 moles, you also need 0.8 mole of sodium phosphate. And to calculate the weight of the sodium phosphate, you need to know the molecular weight of sodium phosphate, which equal 164 grams per mole. So now you can calculate the weight of sodium phosphate. You have to calculate the weight because it's the only thing that you can measure to put the sodium phosphate into the beaker. So it will be equal 0.8 moles times by the molecular weight, 164 gram per mole. And this will give you 131.2 grams. So first, you need to weigh 131.2 grams of sodium phosphate and put into the beaker. So I want to explain more why we need 0.8 mole of sodium phosphate here. So if you follow by this reaction, 1 sodium phosphate will give you 3 sodium ion and 1 phosphate, right? So if we want 0.8 mole of phosphate, so it means that it has to come from 0.8 mole of sodium phosphate. That's why we want it to be 0.8 mole of sodium phosphate here. So the sodium phosphate that we have with us, we don't know the pH of this solid substance, but obviously is very, very basic. So in step 1 of determine the amount of proton that need to be used to decrease the pH, you can assume that at very beginning you begin with 100% of phosphate ion. So for step 1, you have to change phosphate PO4 3 minus back to HPO4 2 minus here. And yeah, you would need the proton to change PO4 3 minus to HPO4 2 minus. And yeah, we mentioned that now we're starting from the very, very basic. So we assume that all the solutions is composed of PO4 3 minus ion. So it means that you need to change one equivalence of PO4 3 minus to one equivalence of HPO4 2 minus. So therefore, we need one equivalence of proton in this reaction. So that is the first step of the second part here. So for the second step here, to partially change HPO4 2 minus back to H2PO4 minus form. And since we already know that we need to use the Henderson-Hasselbalch equations to determine the ratio between these two species, and so we're gonna follow by the calculation that we did before for the Henderson-Hasselbalch equation. At pH 6.9, your solution will contain H2PO4 minus 0.67 equivalents, while containing HPO4 2 minus 0.33 equivalents, right? So back to these questions. At step 2 here, we're starting from one equivalence of HPO4 2 minus, right? And you have to calculate the amount of proton that you're going to add in order to make H2PO4 minus 0.67 equivalents here. So if you want to make 0.67 equivalents of H2PO4, you would need 0.67 equivalents of proton to react with 0.67 equivalents of HPO4 2 minus. So that's why the amount of proton here will depend on the ratio of acid species here. So as we follow the process of how to focus which ratio to work on, in this case, you have to focus on A ratio here, right? And so it means that in total, from step 1 and step 2 here, total equivalence proton would be 1 equivalence plus 0.67. So it's 1.67 equivalence of proton. And again, this is equivalence. So we need to calculate the mole of proton by times the equivalence with the moles of the phosphate ion, because everything needs to comparing back to phosphates, right? So you get 1.336 moles And again, because this is moles, but you need to come up with the volume of hydrochloric acid. So to calculate for the volume of hydrochloric acid, you just use the mole that you need divided by the concentration of hydrochloric acid. And this case is 1 molar. So the volume of hydrochloric that you need to put in the beaker is 1.336 liters. So back to the beaker here, we first put the powder of sodium phosphate into the beakers. 31.2 grams. And then we add hydrochloric acid, 1.336 liters. And then last part here, top up with water until reach 40 liters.